Now to introduce our chief guest and keynote speaker who will be joining us online and I would like to invite Professor Indika Karunathilaka to introduce our chief guest and keynote speaker.
Prof Malik Pieris, our chief guest during this event. Professor Pieris, would you mind switch on your video so that all of us can see you? Professor Malik Pieris is a proud son of Sri Lanka. He graduated from University of Ceylon with MBBS honours in 1972 and received his doctoral training in virology at the University of Oxford in 1981 and training in clinical virology at Royal Victoria Infirmary, Newcastle upon Tyne, UK. His special interest is in emerging viral disease in the animal-human interface, including influenza, coronavirus, SARS and MERS. His research has provided understanding on the emergence and the pathogens of 2009 pandemic H1N1 and avian influenza as well as SARS coronavirus 2. In 2003, he played a key role in the discovery that novel coronavirus was the cause of SARS, its diagnosis and pathogenesis. Professor Malik Pieris is currently the chair of virology and Tam Wan Chin Professor in Medical Science at the School of Public Health, University of Hong Kong. He co-directs the prestigious WHO Influenza H5 Reference Laboratory. He has several accolades to his name and multiple research publications, a Fellow of Royal Society of London, and a Foreign Associate of the National Academy of Sciences in USA, and Chevalier de Legion Honor of France in 2007, Mahathir Science Award, Academy Science Malaysia in 2007, and Silver Bomania Star, SBS Hong Kong SARS in 2008. In 2006, Time magazine selected him as one of the 63 Asian heroes of the last 60 years for his contribution to the control of COVID and infectious disease epidemics. In 2008, when Professor Lalita Mendis was the president of Sri Lanka Medical Association, I had the privilege as a secretary of SLMA inviting him as a guest of honor for the 2008 annual academic sessions of Sri Lanka Medical Association. And that was 12 years ago. And today, as a president of SLMA and vice president of APAC, I have the honor and privilege of inviting him virtually as a chief guest of the inauguration of APAC 2020. Over to you, Professor Malik Pieris.
Thank you. Ibowan, good morning and good day to all of you. I hope my speaking volume is sufficient. If not, please let me know and I will use the headphones. First, I would like to thank the conference chair, Professor Indika Karunathilaka, and the organizing committee for inviting me to take part in this meeting and to deliver the opening keynote. Let me now share my screen. And so what I want to talk about, and I thought would be appropriate to talk about today, of course, COVID-19 is the theme of the day and theme of the year, and probably for the next year or two to come. And since we are talking about public health, what I wanted to focus on, since I'm a scientist, I'm a virologist, is the science underlying public health interventions. Now, I would like to start by just reading for you this article that came out in the prestigious journal Science. It says, the pandemic which has swept around the earth has been without precedent. There have been more deadly epidemics, but they have been more circumscribed. For example, Ebola in West Africa. There have been epidemics almost as widespread, but they have been less deadly. For example, the H1N1 pandemic of 2009. Floods, famines, earthquakes, volcanoes, I might add tsunamis, have all written their stories in terms of human destruction, almost too terrible for comprehension. Yet, never before has there been a catastrophe at once so sudden, so devastating, and so universal. Now, this clearly applies to the COVID pandemic, but this was written not in 2020 and not about COVID-19. It was written about the 1918 Spanish flu pandemic. And I think it is even more interesting to read the rest of the article. And the author says, the factors that stand in way of prevention. He highlights public indifference and confusion, in part attributed to the range of severity of the disease, ranging from asymptomatic to mild to fatal. He identifies the infection is projected into the air, pollutes the hands and the environment unconsciously, invisibly, and unsuspectingly, exactly what we have today with COVID-19. And he points out that prevention devolves on the infected person to prevent spread. Those vulnerable can do little to protect themselves. And finally, the disease is transmissible before the person is aware he is infected. So indeed, over 100 years ago, the past major pandemic that we faced of a comparable scale, these are the comments that were made, which remain true up to today. And I suppose it is also useful to reflect humbly that although the last 100 years have seen so much of advances in medical science, vaccines, antibiotics, and so many other aspects of improvement, still a simple virus can effectively bring the world to a standstill, as COVID-19 has done. Now, I won't dwell on the statistics. I'm sure you're quite familiar with it. This just indicates the number of virologically diagnosed cases, 65 million, and the regions of the world that are particularly affected. To some extent, the Asia-Pacific region is not the worst affected, but certainly affected bad enough to cause huge impact to society, the healthcare system, and our economies. And here is the number of deaths. Again, virologically confirmed, 1.5 million. And I would just like to compare that with the estimates for annual deaths with seasonal influenza, which ranges from 200,000 to 500,000, because there are people who say that, oh, COVID-19 is just another flu. It is not just another flu. And also to point out that these estimates for influenza are not based on virologically confirmed cases. If it were, it would be a tiny fraction of this 200,000. These estimates of influenza mortality is based on statistical modeling. Now, I'm sure the true case fatality associated with COVID-19 is much greater than 1.5 million. And of course, as you know, there are factors that affect regional mortality, such as the age structure of the population, and of course, in terms of reporting, underdiagnosis. Now, as I said, I want to focus on just a few examples of the scientific basis for policy. So first, let's look at the infectiousness profile of this virus, SARS coronavirus, the cause of COVID-19. So back in early February, we published this data, which we had accumulated in collaboration with colleagues in southern China, in Guangdong, showing that the viral load profile in the upper respiratory tract in COVID-19 is maximal at the time of onset of symptoms and then gradually declines from there onwards. Very different from SARS, where it was very low during the early 4 or 5 days and increases subsequently. So in that paper, we said that SARS coronavirus resembles influenza and will require strategies very different to those that were successful in the control of SARS coronavirus 1. And indeed, this is work from our epidemiologists at our School of Public Health. And they were able to show, looking at a large cohort of patients from China, that about 40% or more than 40% of transmission takes place before the onset of clinical symptoms, which is this point here. And then the bulk of the rest of the transmission takes place in the next 4 or 5 days after onset of clinical symptoms. So the damage is done before the patient even knows that he is sick, and the first few days after he develops symptoms. And this is again confirmed by other studies, for example, where they have looked at contact tracing, and again showing that the transmission risk was greatest in the first 5 days or so after onset of infection. So this is the reason why containment of this pandemic is so difficult. Now, how is COVID-19 spread? Our understanding of it is that it is primarily spread by the respiratory route, these large droplets that fall because of gravity within 1 or 2 meters, and fine airborne particles that can spread for a longer distance. But as you can see here, that as these large droplets or small airborne particles, as they leave the infected person's mouth, they do get diluted. And so therefore, distance plays an important role in the probability of getting infected, because you need a minimum infectious dose to initiate infection. A single virus particle is unlikely to initiate infection. So that is important to understand. Then, of course, there has been a lot of debate as to whether, in the case of coronaviruses, whether it is large respiratory droplets or fine aerosols that contribute to the spread of infectious virus. So fortunately, we had been doing some studies on influenza in the previous years, and some of those patients were not influenza, they were the seasonal coronaviruses, not COVID-19, of course. And I'm showing you the data from the seasonal coronaviruses. And what you can see is that these patients, when you monitor their breath or their coughing, they shed infectious virus both in the large droplet fraction and also the fine aerosol fraction, as you can see here and here. But most importantly, when these same patients wore surgical masks, the amount of infected particles leaving their respiratory tract, leaving their mouth, essentially was brought down close to zero. So this, together with the realization that COVID-19 is transmitted even before patients develop symptoms, that is the pre-symptomatic phase, and even from those asymptomatic individuals, this is the understanding that led to the recommendation that for the use of surgical masks more widespread in the community. And indeed, now there are epidemiological studies that support, provide evidence for the impact of the use of surgical masks or face coverings of any sort in reducing transmission. So this is a study from Germany where they have shown quite substantial impact of the mandatory introduction of face coverings in reducing transmission. Now, in addition to the airborne spread, there's also the potential for fomite or indirect transmission in the spread of COVID-19. So we looked at the survival of the virus in the environment. And what you can see here is the SARS coronavirus 2. And you can see that in smooth surfaces, such as stainless steel or glass or plastic, the virus survives live, infectious, for many, many hours after the virus is deposited on those surfaces. On the other hand, on material like wood or cloth or paper, virus survival is much shorter, a matter of minutes or an hour or so. Now, if you compare this long survival on surfaces with, for example, influenza, influenza is dead within a matter of an hour of deposition on a surface, whereas COVID-19 and indeed SARS-1 could remain viable for many, many hours. So the potential for indirect transmission is quite real. Now, for indirect transmission to take place, you also have to have the virus surviving on the hands of the patient or the person. Now, obviously, that's a very difficult experiment to do ethically, but recently, colleagues from Japan have used some novel technology to essentially show that the survival of SARS coronavirus on the skin is much longer, again, compared to influenza. So taking these two together, it would be, I would say, providing circumstantial evidence for the possibility of transmission through fomites and through hands. So just to summarize then, we know the routes of transmission through the airborne route, through close contacts, and through the indirect route in fomites. And as I pointed out, the issue of dose and dilution means that distance is important in reducing the risk. Ventilation is important in reducing the risk of transmission. I pointed out that face coverings, there is evidence to show that that reduces the risk of transmission. And hand hygiene, although there is no direct evidence for reducing risk, this circumstantial evidence is very strongly in favor of the possibility of transmission taking place in this route and its importance in breaking transmission. Now, another question, of course, is the duration of infectiousness once a patient is diagnosed or once a patient is symptomatic, because this is important in terms of how long the patient needs to be isolated, particularly once a patient is hospitalized. So this is a study that we did in Hong Kong, and each of these dots that you see here is an individual patient and the viral load by PCR in this patient. So you can see that some of these patients are shedding PCR positive virus for quite a long time, 40 days, 50 days, 60 days. But the red circles is those specimens from which we could culture infectious virus. So you can see two things. Firstly, infectious virus is culturable only within the first 8 or 9 days after onset of clinical symptoms, and only in those specimens which have a very high viral load, over 1 million virus particles or so. So this means that infectiousness is not equal to PCR. So PCR positivity does not necessarily mean that you are detecting infectious virus. And it's not just our study. There's been also a much larger study from the UK, where essentially with the same conclusions that infectious virus is found early in the illness and in patients with high viral load. But of course, in patients who are severely ill or who are immunocompromised, they may be infectious for a much longer period of time. So it is this information that led to a change in policy of discharge in many countries, including in Hong Kong, in Sri Lanka, and WHO, that patients after 10 days or so after onset of symptoms, once their symptoms have resolved, they can be safely discharged. Now, this realization also has other implications for control. And this is a very interesting editorial or a commentary written by Michael Mina in Harvard. So this just shows the kinetics of viral load here. And of course, the period of infectiousness is this period, which is associated soon after onset of symptoms and the period of highest viral load. But PCR positivity may be positive, as I showed, for much longer. So this is important when you're thinking about policy of interrupting transmission, which is a different question, if you like, from diagnosing a patient and treating a patient. When you're focusing on interrupting transmission and, for example, doing diagnostic tests to interrupt transmission in the community, this realization is important, so that what you really need is to find patients in this phase of the illness those with high viral load. And this is why, although PCR is the most sensitive diagnostic test that we have, some of the better and, for example, WHO approved and antigen tests and rapid diagnostic tests do play a role. And again, this is another paper where they talk about the impact in terms of transmission on the sensitivity of a test, the turnaround time to results, and the frequency of testing. And what they find in this analysis is that it is not the sensitivity of the test that is most important in terms of interrupting transmission. So again, it's important understanding that we need to use the different tests that we have available in an intelligent way to impact on the question that we are trying to address. Now, of course, vaccines are on the horizon. We are very fortunate that it seems that many of these vaccines do seem to be effective, at least the 3 that have provided phase 3 clinical data so far. So it is useful also to just recapitulate on previous viral vaccines. So as you know, classically, the approach to a viral vaccine has been to grow the virus, kill it, and inject it. And examples are the killed polio vaccine, the rabies vaccine. The other approach to viral vaccines has been to attenuate the virus, make the virus weaker so that it doesn't cause disease, but it still can infect and induce an immune response. So as you know, this includes vaccines like measles, oral polio, mumps, rubella, varicella. And then you have vaccines based on individual components of the virus, proteins of the virus. So examples being hepatitis B and HPV. Now, more recently, of course, there have been RNA vaccines where what we are talking about is instead of injecting the protein, we inject the RNA that codes for this protein. And then, of course, you can also inject the DNA that codes for the RNA that codes for the protein. And you can use another approach to deliver this, the gene that makes the protein into the cell using a replication incompetent viral vector, such as the adenovirus that is being used in some of the vaccines. So by these strategies are basically making the cell become the vaccine factory, if you like. And it's quite important for communication because, again, there's a lot of misinformation out there. It is important to be very clear that these RNA that is injected will not get integrated into host DNA. The cell has no mechanism to convert RNA to DNA. So there is no risk that this RNA is going to alter your DNA in any way, because this seems to be a misinformation that is going around. So how do the COVID-19 vaccines fit into this framework? So the Moderna, Pfizer, BioNTech vaccines are RNA vaccines, as you know. The AstraZeneca uses AstraZeneca, the CanSino, the Gamaleya, and Janssen. All these vaccines use this adenovirus vector strategy, but importantly, they use different adenoviruses to deliver the protein RNA into the cell. And there are differences, theoretical differences in these. The problem is that if you use a human adenovirus like adenovirus 5, many of us will have pre-existing antibody, which may compromise the success of that vaccine, whereas the chimpanzee adenovirus, because humans have no prior immunity, is likely to be more successful, etc. So anyway, the phase 3 trials are the thing that will tell us the final answer. Then, of course, there are traditional vaccines, such as killed vaccines like Sinovac, and there are protein vaccines coming along as well, Novavax and the Sanofi GSK. But having said that, and as I pointed out, it is really fantastic news that at least the first 3 vaccines, phase 3 trials that have come out do seem to be very promising. But we just need to think about what we can expect from these first generation COVID-19 vaccines. It is important to note that the endpoints in these phase 3 clinical trials is protection from disease, not prevention of transmission. We cannot assume that a vaccine that protects from disease necessarily will equally protect from transmission. So if you just look at this situation here, when you have natural infection, you have the virus infecting your nasopharynx and your lungs, you will develop immunity in your nasopharynx and in your lungs. And you are likely to be protected from disease, but also from infection in the nasopharynx and therefore prevent transmission. If you have an injected vaccine, what you have is antibody in the blood, which will quite likely protect you from severe disease, but it may or may not prevent virus colonizing and replicating in the nasopharynx. So this is why we need to be very careful when we are thinking about what you expect these first generation vaccines to do. Now, there's a lot of talk about population immunity, what is popularly called herd immunity. Now, at the moment, as I pointed out, there is really no evidence that the protection that we are seeing, which is extremely welcome and which will protect the most vulnerable in our population from severe disease, whether this will translate into prevention from transmission. And it's important to keep that in mind. And I think in one of the opening comments, talks, it was pointed out that we really have to, it's not just the science, it's not just the public health. We really have to think about social and behavioral aspects and behavioral science when we are trying to control a pandemic like this. And I won't go into the details here, but as you can see, the issues of communication, miscommunication, the social context, the importance of leadership, and in the perception of the community about the threat are crucially important. And I think we need to learn from our behavioral and social science and anthropological colleagues in how best to communicate effectively. So if I summarize the key points that I was making, I think we need better preparedness to confront emerging infectious diseases. When faced with a novel pandemic as this one, in the initial stages, non-pharmaceutical public health interventions is all we have, but our knowledge on the mechanisms on respiratory virus transmission and the effectiveness of non-pharmaceutical interventions is still suboptimal and poor. And I think we really need to pay more attention to the science base behind this evidence. I pointed out the value of diagnostics and how we can best use them in terms of achieving the public health goals that we want to achieve. The importance of communication and rebutting miscommunication that is taking hold. And of course, again, a point that was made in one of the introductory comments, the need for strong public health systems. I think if nothing else, this pandemic has really shown why it is fundamentally important to have strong public health systems and therefore have the investment in building and maintaining these public health systems. But then in the last slide, I just want to go beyond pandemics. The pandemic, COVID-19 is bad, it's terrible, but ultimately humankind will survive this. But I think we have much greater issues in front of us. What the pandemic has shown us is that science has been telling us to expect such a drastic event such as a pandemic like this, and policymakers, politicians, economists ignored it until it was too late. But there are other things that science is telling us, and that is that we are living beyond our means in terms of planetary sustainability. And I mean in terms of ozone layer depletion, in terms of climate change, in terms of nitrification, in terms of biodiversity loss, in terms of air pollution. And in nature, nothing grows forever. This is a law of nature. And success, economic success, as defined as annual increase of GDP, is unsustainable. It makes no sense if you think about it. What we really need is human contentment, happiness, and well-being, not just percentage increase in GDP year on year and assuming that this is benefiting our populations, because we really are at risk of rupturing the limits of planetary sustainability. And as you can see, examples of massive climate events huge pollution, loss of our environment. And I think COVID-19 is a great teaching opportunity to raise awareness that we cannot ignore the risks that science has been highlighting over the past decades. And this particularly applies to these issues of planetary sustainability that I was talking about. So with that, I will end. This is an image taken from one of the Apollo flights from near the surface of the moon, showing the Earth. And you can see the barren wastelands of the moon and that beautiful planet that we call Earth. And we really have to realize that this is a precious resource. And in terms of public health, in terms of human well-being, we really have to pay attention to safeguarding this fragile ecosystem. Thank you so much for giving me the opportunity to talk to you today.
Thank you very much, sir.